First of all, I want to thank you that I can present some of our work here. I'm talking about a non-invasive determination of internal traits of wheat ears using computer tomography. So we heard in the talk before, thank you, Uli, for making all the motivation why seed phenotyping is so important. So, I mean, when you phenotype the seeds and you do it manually, it's a huge time invest. So you have to collect them, you have to count them, you have to measure them, and you can get a lower time invest when you go for a single seed analysis like Uli presented with the phenoseeder, where you can have like an automatic analysis of single seeds in there. We used CT, computer tomography, for seed analysis also. To give you just a short explanation what we mean by X-ray computer tomography. We have, on the left-hand side, we have an X-ray tube where the X-ray is coming out. We're going with the X-rays through a box of seeds, and on the right-hand side you have the detector, which takes the images of the sample. We need to rotate the sample by 360 degrees to have from each angle an image and a 2D projection, and then you get, from this you can calculate a 3D reconstructed volume, which means you have then afterwards at each position in the volume your density of the density information of the object sample. We take for such a measurement around 1,200 images, so it's like a slow rotation and acquiring images in that. So what you can do, you see on the left-hand side the reconstructed volume of barley seeds. We do have then the image analysis queue afterwards to segment the seeds individually. So on the right-hand side, you see each seed has a different gray value, which means they are detected from the algorithm by their own. So on a single seed level, we detect the seeds and we can calculate the traits afterwards out of that. So like the shape or the weight and the density and whatever you want. So we asked our question, why do we start with the seeds? Why we can't just start with the ear? So then we could to save more time in doing the image analysis, because you don't have to dress the seeds, you don't have to put them in a box, you just use the ear. So we did that. As you can see here, that's a 2D projection of the ears. There are 4 ears on the image you can see. And as you also clearly see that the ears does not fit to the image completely. So what we did here is during the rotation by 360 degrees, we also moved the axis upwards, which means we had a helical setup for the X-ray CT to get the full ear at one measurement and have afterwards the data there. We put in there 4 ears, as you can see, because it just fits in there, and it also saves time when you do 4 at the same time. So here we did this with the small CT. It's like you can put it on a table, and you can also use it and bring it wherever you want. So you can see on the image the 4 ears, and it's a vertical slice through the image, through the reconstructed volume. And you see that there are the seeds within the ear, and you also see the hairs of the ears. And on the right-hand side, you see the sample holder where we just stuck in the ears in there. So now we have the images. So what we did, we have the 3D volume, as you can see, rotating the ear, you have a fully reconstructed image. You see on the right-hand side, on the left-hand side, the slice, a vertical slice through the daters, and you see also here that we made measurements of ears with drought stress and without drought stress, just to see how we can image the daters. We can measure ears with that system up to 20 centimeters length in a resolution of 31.25 micrometer voxel size, which means, you know, from a 2D image, a pixel, and in 3D it's a voxel, so it's a cubic, and the voxel size is then 31.25 micrometer. The measurement time per ear, so I just divided by how many ears I had in the measurement time, is 7 minutes. And the X-ray parameters are 90 kV and 80 microamps. And the exposure time was 500 milliseconds. So the X-ray parameters are quite low, so there's not so much exposure on the ears. So now we have nice images, what we can do with the nice images. We did automatic image segmentation. So on the left-hand side, you see the measured daters, just one slice of the measured data, so that's not a full volume. And then we developed an algorithm which can figure out which seeds are in there and find the individual seed within the ear. And they are marked in some colors. Oops, sorry. Where's the pointer? Ah. So you see here the different colors, which also indicates that each seed is detected by the algorithm. And then we just orientate the seeds that they are all in the same orientation and make an image just for the user to see how the algorithm, if it's good or not good, to have a reaction on the daters, where the seed has the biggest diameter in size. So as you can see on the image below here, these are all the seeds which we found in the ear, and they are all in the same orientation to see how it will look like. To give you an overview what the algorithm can do and what different types of ears they can measure, we measured 290 ears, and here are some examples of different sizes and shapes. So you see on the left-hand side the more fully developed seeds, and on the right-hand side they're getting worse in development. But also for the really small seeds, we all detect every seed in there. So what we did is we threshed the ears afterwards, counted the seeds, weighed the seeds to see how good the algorithm is working. And yeah, as you can see, it also doesn't matter if the ear's not straight, and even more bounded ears can be measured with that algorithm. Here are some examples of the overview images, and you see on the top left, that's, I would say, pretty easy because they are really big, they look nice, and you have good seeds. And then the image below on the left-hand side, it's a little bit more challenging, but the two right images, they are really small seeds. So the size you see here, it's not the actual size, it's just a little bit stretched so that each seed has almost the same size, but they are really small and tiny. So for the algorithm, we did 4 different classes of the seeds. So we have the size 1, which are the full developed, nice wheat seeds. Then we have a class 2, 3, and 4 is the really small, tiny seeds where we normally when you sieve the ears or the seeds afterwards, they will fall through the sieve, and we normally don't collect that as an actual seed, but they are there, and they are also going to the weight. So we segment them and see them there. So what kind of traits can we calculate of that? So with this algorithm, we calculated the size in cubic millimeters. We calculated the number of seeds per ear, the spherical ratio of the seeds, so you know how elongated they are or how round they are, the mean gray value, which gives you a quite good approximation about the density, the center of mass, so you also know where are the seeds placed in the ear, so you can also have a distribution about the size of the seeds over the space. Then you get the minimum covering sphere radius, which gives you the radius of the main or the maximum diameter of the seed, and also the center of mass of this minimum covering sphere, so you know if the seed are stretched and a little bit has a different center of mass than the center of mass of the seed without the covering sphere. You get the number of voxels of the surface, which gives you a good approximation how deep or how wide the crease is in the seed. So you have also information about the surface. We get the spherical ratio sphere radius, so which means you have the radius of the sphere with the same volume as the seed. And we get also a virtual, or we call it virtual seed weight, because it's we not actually put it on the balance to weight it. We calculate the weight out of the daters. And to give you some results on that, I will give you the virtual seed weight, and we go for the number of seeds per ear. So as you can see here, the correlation between the measured weight and the virtual seed weight is quite high, which means we have a 0.988 correlation in there. And we were pretty happy about that, because it's really a good data set to see that it actually works, and it's also not only working for the full mature ears, it's also working for the drought experiments in there. And the other comparison was the number of seeds. Here you see there are not all of the ears in the diagram. That's because when we calculated the daters, we didn't realize that we maybe should also calculate the small ones which were going through the sieve. So that's only the daters where we have all seeds counted for the ears. And again here we have also a high correlation in that. So to come to a conclusion, computer tomography is a good way to save time in seed phenotyping. It's also open additionally access to not optical invisible traits. So you see also traits like the structure within the seed, which you have not no access when you measure optically. And measuring the whole ear enables to segment different sizes of seeds. So it's not only the big ones, you can also segment the small ones. We can determine the virtual seed weight, and the correlation between the virtual seed weight with the measured seeds are really high. And another good thing is that the segmentation is all automatically done. So once you have the data, there's image queue to get the results afterwards. And it's calculated on a single seed base. So it's not a mean value over the whole data, so you have for each seed within the ear the traits. We have also an idea to speed that up, because 7 minutes per ear is also a long time. You can use a fully integrated system like this one is made for tuber plants. So you put in there then a bunch of seeds, and then you have a measurement time of 10 seconds per ear, which really gives you a good opportunity to have an automatic analysis of seeds within the ear. If you want to know more about this, you can go to the poster of Stefan Goerth. It's the 74. Here you see like the plant is rotating within the X-ray system, and then it's going out again in the fully integrated system. Yeah, the XI is our detector. Yeah, and then going back to the loading station of the plants. So I want to thank you, Jessica Schmidt and Trevor Garnett, who did with us the data, or we get actually the ears from them, and they helped us with the measurement. And they are funded for this project by the WETAP. And from our institute, it's Norbert Wörlein, Anja Eggert, Norman Ullmann, and Stefan Goerth, who did the work with me together. Thank you.
Thank you, Annie.